As you saw in the previous video, there are lots of ways in which we can define a neighborhood, and GIS tools give you a tremendous amount of flexibility in this regard. This flexibility causes a problem we refer to as the multiple areal unit problem. As you recall, this map shows the census tract and zip code that my old apartment was located in. Now I've added a half-mile radial buffer definition of neighborhood over the top. And now I have added the half-mile street network buffer. And so we have four possible ways in this example to define my neighborhood. But this multiplicity of available spatial units presents a problem, because when I analyze data to assess if some neighborhood feature is associated with a behavior or health outcome, the results I get depend in part on which neighborhood definition I choose to use in the analysis. This is the multiple areal unit problem, also known as MAUP. I'm going to walk you through an example of MAUP. I'm interested in whether the urban design concept of neighborhood walkability predicts engagement in pedestrian activity and, in turn, lower body mass index. Walkability refers to a set of urban design features that support active travel and includes population density, street network connectivity, land use mix, availability of destinations that support daily needs, and public transit availability. Neighborhood population density is one-dimensional walkability, and across studies, higher neighborhood population density is associated with lower body mass index. On the right side of this slide, I am showing results of analyses of BMI data from around 14,000 New Yorkers as predicted by population density. For each of the 7 analyses, I use the same study subjects and the same covariates in the regression model, but I estimate neighborhood population density for each subject with a different definition of neighborhood used in each analysis. At the bottom of the chart, you see the results for census tracts, then zip codes, and increasing sizes of radial buffers and one network buffer as you move from the bottom to the top of the chart. In each analysis, the beta coefficient relating differences in population density to differences in BMI is negative, and the confidence intervals do not include 0. So all the analyses agree that higher compared to lower population density is associated with lower BMI. But you see the point estimates are different across each analysis, with a trend of the beta coefficients getting further from 0 as the size of the neighborhood definition increases. So if you were to do a cost-benefit analysis for plans to increase population density, the results would depend a lot on which of these analyses you chose to use in your cost-benefit analysis. Another way to look at this is you could do your analyses over and over again using slightly different neighborhood definitions until you found one that produced a result you liked, and then you publish that result. So again, when you read a neighborhood effects research paper that reports results based on neighborhood measurements created using some neighborhood definition, you should ask yourself, why was this definition used? How does this concept of neighborhood relate to the exposure disease process that the authors are studying? Because remember, when you do analysis, you can get quite different results depending on how you've defined the spatial scale of neighborhood in your data set.